I'm going to talk about the AMPEL platform. Analysis on tap. What does that mean? We'll get back to that. We could talk about acronyms, but we don't have to, so let me skip that. And instead show my one slide actually containing science. This being the last talk, having had lots of presentation, means that practically all of the science has already been discussed. So I summarized it here, kind of my science interest, and my goal is to kind of tie them together because they're quite different. Yesterday, Jesper talked about optical supernovae. They're exciting in many ways, especially what I want to do. One thing is to find transients very, very early, so extremely close to the explosion time when you're covered in noise. So I have to find out very good selection algorithms, because what you want to do is to send a trigger to some robotic follow-up telescope, and they don't like when you send noise or something that's already gone to them. So that's fun. Then of course we're going to find these unique transients like the gravitationally magnified supernova that you also saw yesterday. Another thing to do with those transients is to find all of them. I want to do that, for example, to map structure in the local universe and see how this moves and see if we can trace, for example, the dark matter distribution. There, of course, is very sensitive to finding all of the events. If you don't do that, you will have a biased results one way or another. And then, of course, the main topic here is discussing various multi-messenger aspects. That's, of course, also fun. You've seen this picture before. This is kind of interesting because that started as two different AMPEL analyses, one by the TDE group. They put in a very advanced model for finding potential TDE objects in the ZTF data. And in the meantime, then the neutrino group had a program to find optical counterparts. So that was discussed by Anna. And of course, what was fun here is that both of these analysis pipelines then selected the same objects. Unfortunately, we didn't see that immediately, but rather it was discovered kind of manually afterwards. But still, these are all kind of fun things that we can do now. And even if the final science interpretation we do are very different, they all have some similarities, is that we have lots of real-time data analysis coming in. We somehow want to select data and analyze that data using some metric, and this metric or some model, and this model is very science dependent. But after that, then we want to take care of that output in some systematic way. And this is then, AMPEL in short was developed as this sort of platform that can host these different kinds of analysis. So a few slides to kind of set the scene for the future. This is all what we know and what also we just discussed. So in the next decade, we will get huge new large data streams. They will not only be large, they will also be very heterogeneous. They will have different fields in there that need to be interpreted in different ways. It's a completely new phenomena coming up here, data reversibility. It will directly influence, for example, radio telescopes where you just cannot save everything that you're getting because there won't be enough bandwidth to transmit the data. So you right at the telescope have to make a selection. So what do I store? What do I not store? And then a similar effect will happen, for example, in an optical data set. Even if we can save all of the data, we have to choose what to react to in real time. And of course, what we don't react to is usually lost afterwards. And we have to do some very painful photometric reconstruction that usually never works very well. And then of course, we have the multi-messenger aspects where that just makes all of this harder because in some sense, you have to every possible combination. We also have kind of new surroundings that I think we should discuss and adapt to. And these are just two examples. So one is the FAIR paradigm, which is kind of coming. It's already, for some surveys, being taken very seriously. I think it's going to be even more so for future missions. I think it's going to be a criterion. And I think most people agree that this is a good thing. and we've made lots of progress in, for example, making data accessible. But when it comes to interoperable and reusable, Ada talked about that. It's very important, but we still don't know how to do it, right? We have green computing. One of what will become an issue is that we just don't have enough energy to do all of the computation, even if we would have the power, or to store all of the data. This, for many of these future missions, this will be a driving kind of constraint in how you set up the survey. So this is another, it will kind of lead to another aspect of data reversibility. We will have constraints, we will have to then understand, so which fraction of our data do we have, and what do we do with that? Kind of both of these things lead to the need for new tools, and this is in some sense the topic of the workshop. So you've seen all of these logos before, and in some sense they all reflect different aspects of this needing new tools to deal with this situation. And it's not only that we need new tools, or we need these sort of processing tool or infrastructure tools, we also will want to do all of this fancy new big data analysis that we kind of, first of all, have realized that we need to say that we're doing that to get funding, but then we actually also now have realized that they're useful. But it's not easy, so we need to learn how to adapt the new data sources into something that we can use with modern statistical techniques. And that often involves creating federated archives that just fits into these kind of modern techniques. Okay, so that's kind of the setting that I think we're all fairly, that we know fairly well. So just a few kind of words of AMPEL, I'll try to demonstrate later. So it's designed as a modular platform for systematically processing real-time data, or real-time or offline data. So one mode is for AMPEL to work as a broker. That's kind of what's highlighted here. You take some sort of real-time data stream, you make a selection, and then you immediately send some live output somewhere. But this is, again, as we see, the core aspect of AMPEL is this aspect of code to data. That is a platform that can lift in analysis pipelines developed by other people, and then this can be exposed by different sort of data streams, real-time or archived, and then create different sorts of outputs. So it's all public, the code is public, and then there's a public instance running in Desy. So that's a little bit the summary I wanted to do, and then for basically the rest of the talk, I'll try to do a small demonstration of a very small analysis of optical data, just to see how this could work. So let's try to find fast declining optical events. This is of course a very exciting class. This is where we find F-bots and, for example, kilonovae, if they exist. So fast declining, that's very easy to define. So we can kind of all, as we used to, write a few lines of Python code that for a set of photo points from the light curve, kind of look at the latest one. Latest ones, look at the time difference, look at the magnitude difference, and define a decline rate. This step is very easy, and this is what we're all used in some sense as scientists. This is what we spend most of our time training for. Take some sort of theoretical ID and write down a model for how that could be captured or quantified. This is, of course, an extremely simple model, but based on this and the modern Python tools, it can, of course, be extended to virtually anything. Rather, the step that's not so straightforward today is what's coming next. So how do you actually connect this to data? How do you share the code? How do you export it? How do you save it? How do you export the outcome of it? So let's see how this could work. I'm going to do this through something that we call an analysis schema. And you can see there are links here. This is, of course, a second kind of problematic aspect of giving a talk, and that's actually showing a configuration file. But I still, since this is kind of the final technical end, I still wanted to do it. And of course, we won't go through all of it. But anyway, it's referenced, it's something that's online, you can go have a look at it there. So analysis schema contains a listing of all the software units that's needed to carry out some sort of pipeline. And internally, we divide that into different tiers. So we can collect data, combine data, then the data is analyzed, and then at the end, you react or aggregate the data in some way. And in all of those stages, you then have different units that can carry out some sort of scientific work. Let's try. Okay, so let's try it out. So this is just what I will be running on my laptop, and let's see if it works. So poetry, so we're running this in a fixed environment, so a Python environment with a log file with versions of these libraries, meaning that hopefully you should all be able to recreate this. And then we're running AMPEL, and AMPEL is then taking on a job, and the core of this job, the schema, is this YAML file that you saw here. So let's run that. In the meantime, I'm going to start a different job. Okay, so this now completed. It did some different stuff, and we're not going to use that in the end. But in the end, it printed out something that looks reasonably close to a VO event. So now what's just printed to the screen, we could have asked it to be submitted to or sent to some event server, but I don't know who would want to receive this. And we don't need to look into the details, but we can, for example, see that there's some magnitude information there. There's some where, when information. And in the end, there's a description that then shows that also this was, we calculated some sort of decline rate, and that was then what motivated this VO event to be issued. Okay, so that seemed to have worked. So now let's go back to this description and see what actually happened. So the core aspects of this configuration file are kind of these three sections here. So first you have a loader, a ZTF archive alert loader. So this is a class that does what it says. So it loads for some specific optical event here. It loads from an archive. It loads the light curve of a ZTF transient. And then in the end, the core, we're calling this little Python method called T2 fast decliner. So what is that then? Let me then go here. So now we're at the publicly published GitHub repository where there is this unit called T2 fast decliner with some documentation. And then in the middle, you can see that this is exactly where we're storing this small calculation that we were doing. And then it's creating an output. This is just a dictionary. And we have some criteria for when something is a fast decliner. So that's all, again, fairly straightforward to construct. And then in the end, we have another unit called the VO event publisher. Again, something you can look up at GitHub. And then what AMPEL actually will do is that it will go through this, these units in sequence. It will start by carrying out this, requesting photometry for this event, and then storing it in the database. In the second stage, it will say, okay, you want to run this analysis unit on this light curve. It will query this computation for completion, and then will carry this out. And then in the third stage, it would take the output of this calculation and schedule it for, and basically create a VO event based on this result. So in some sense, in these little steps, we have, in a very minimal way, but still completed an analysis of an optical data, maybe a recognition of a kilonova. what do I know? Okay, so this worked fairly well, but it's also in some sense more cumbersome, right? We don't really like configuration files. So what's the point of doing this? So that's what I'll spend a few slides discussing, because in my mind, this is kind of the regime where we have to go to do real-time analysis in this future decade of all of those complicated services that's going to throw data at us. It doesn't need to look exactly like this. In some sense, there is nothing. This is a format that's used internally by AMPEL. It can have different formats, but the overall structure is, I think, something that we will be adapting. So the why do it? So the first kind of obvious reason is scalability. So now I ran the analysis on one single light curve on my laptop. That of course works. But if I want to carry out this analysis on the full ZTF alert flow, that's not something I can do here. But the advantage of analysis schema is that I can be sure that it works the same way everywhere, meaning I can upload that to a computer center live instance that can take care of, that can make use of parallelization and so on. You can actually run this unit on the full ZTF alert stream and then really react to really fast declining events. So it does allow you to do local development of analysis like we've kind of always, what we've been used to doing. And then once you're ready, you can transfer this code to some sort of execution and production environment where you can make use of all of the advantages there and of course just the alert streams. And things like deduplication, meaning that common operations are only being done once and so on. Another kind of immediate advantage has to do with reproducibility and things that come with that. It's straightforward to take this analysis schema, bundle it together with a specific software version and distribute it, for example, with your publication, meaning that anyone can then redo your analysis. You don't have to answer all of these questions. How was it actually done? It, of course, directly ties into these FAIR standards, makes this much more straightforward. There are also in AMPEL, when you process that, there are direct kind of provenance features, meaning that you log everything that's being done. And then having this sort of kind of starting point for analysis makes it much easier to work, for example, with selection effects. It's very easy to widen your range or change the parameter settings, rerun it, and then compare versions. This is possible just because you can capture a full analysis in one configuration file. And something I also wanted to mention here is that explicitly data access rights are separated from the analysis pipeline. So as we just heard, data access right is a major thorn in much of astronomy and astrophysics. And it's actually better, it's worse in other fields. So we're starting talking to people in biology and so on, and they have similar needs, but there it's even worse. So for them, what we're having is kind of still very good. So here, I just want to make the point that the analysis pipeline, so what data requests are separated for your data access right. So how this would work is that when you run a specific analysis, which data you would actually be exposed to depends on what data rights you have as a user. And still, I don't like it, but as long as we have private data set, there's no way to get around that. At least in this way, you can publish an analysis, a software analysis, and then eventually when data become public, also the full analysis steps will be available. Another way that this way of working where it creates advantages is modularity. So as you saw, we quickly wrote this T2 fast decliner unit that just made a very simple scientific complication. But we didn't actually have to know much about how to access the CTF archive or these PESCO VO event standards. we had to know that there were units that could do those conversions for us, and then call them, and then we're pretty much done. That's, of course, an immediate advantage for users. But there are kind of even more, I mean, I think even deeper advantages that I'll get to, I think, in the next stage. Oh, no, first, I'll make this demonstration first. So here we use the CTF archive alert loader to download the light curve of a single event. So when I started a different AMPEL job in parallel, I carried out exactly the same analysis schema. I just changed the alert loader to instead grab one of the 03 gravitational wave alert contours. And of course, you know Grace DB, so this is grabbing one. This is one of the smaller regions, but still, I was able to download the map and process, and also then download CTF alerts corresponding to this contour within some time range, and then apply the same analysis schema to all of those alerts as well. So let's see if that actually. Okay, so Grace DB, we're not. Let's try that again. That's what happens. But I did run it during the previous talk, so you can actually see how it works. So here you can see we're processing lots more alerts, but in the end, we actually did manage to find one event that were associated to this Grace DB contour that had an alert emitted right at around time, and that were declining in the R band, and we even generated a VO event for this detection. And in principle, this is a kind of a limited but still existing gravitational wave multi-messenger analysis. And in some sense, you could go and make this active and run it for 04 and be part of this fun exercise. Let's see. Okay, and now that's also completed. Okay, so that's modularity. And then that's deeply connected with the final point here, which is software development. That this way of strictly separating an analysis into real-time analysis into different modules allows us to take software development more seriously. And this will be one of kind of the main challenges for how we work, at least coming from the astronomy side. I think the astroparticle sides, they are much more used to larger collaborations and building kind of a uniform pipeline. In a lot of astronomy, that just doesn't exist. But that's something we have to learn. And we have to, for these projects that will be running for a decade, we have to learn to also write software that we can gradually improve and maintain. And kind of the key point here is to recognize scientific software development, because that's something that we're doing a very poor job at now. I mean, most of the kind of key tools that I'm using now, the best tools that were developed by people who wrote very good software, but just because they did so, they never got a job in academia. So they are now out doing something else. While if they could have stayed, they could have continued contributing. So this is something we could, that we would recognize, and this sort of work methodology where a scientific software developer publishes a module that can then be used online, that can be requested to be used by the community, they can then go back and say, listen, I developed the T2 fast decliner unit, which has now been used, and then directly quote, it's been used 2,000 times or 2 million or 2 billion times in the analysis of 04 data, and it led to this many papers. So this is also a way to kind of get started with that process. So there are, of course, disadvantages, again, even stronger for the astronomical community. And it all has to do with kind of reversing the work order that we used for astronomy for at least a few hundred or thousand years. So in that you actually start with defining goal, hypothesis, theory, and after that you do your software engineering and development. And then only after that you expose this to the full data. And this goes kind of against intuition of at least most people that I'm working with. But it's just a way that we have to change how we're working in order to really use these new data sets that are coming. So this, we had to develop some conceptual solutions. I will skip them now. And instead kind of, from that short demo that I hope some of that I hope will stick, that these kind of solutions are possible. It takes work to develop a real-time analysis into an independent analysis schema, but in the end, you get a ton of benefits from it. So now I just, for the last kind of minute or so, I want to talk a little bit about the Sciathlon. I'm very happy to be here, and for me, kind of the main part of discussion might be today or tomorrow. We can discuss how we actually go further. So these were just some random thoughts from this morning. So one kind of question that I really have no idea how to answer is we will be seeing all sorts of streams that are coming from different distributors, and some of them will have a common origin, like the alert distribution from some of the large facilities. Some will not. So how do we keep track of all of these streams and the events that are in them, where the labeling scheme will obviously be different? And kind of a hard part there, and that's going back to some of the things that I think are missing in the view event format right now, is that how do we well describe what was done, so what pipeline operated on what data in order to get what output? That's currently not easy to summarize. Then we have the question of format and exchange, that in some sense I think those should be easy things to just agree on. Let's see if it works. And then of course, I think it would be very interesting to see what sort of information would you like to see in Astro-COLIBRI, right? Would you, because for a lot of cases where a lot of model calculations that we're doing, a lot of figures are in some sense already being computed in a real-time basis in AMPEL and also in other brokers. And it's a question of which ones would actually be useful to see and how should they then be displayed in Astro-COLIBRI. So those are some things. So I'm just going to end. Kind of the main point is up there that we will need to invest in software engineering to really make use of the very, very exciting data sets that are coming. And that's kind of also I don't know, I think that's also directed to students. This is really something that's needed. It's also challenging, and because it is the question, so how do you get recognized when you do that field? At the same time, it's kind of the people who actually manage to do that well for the upcoming surveys will be the ones that actually contribute the most to science. And then some words about AMPEL. So it's a public tool for executing analysis schema. It can be applied to real-time data, and you can run it locally. So these are just install instructions that should allow you to run the notebook or the analysis schema I just demonstrated. And then these can be uploaded to, for example, the live instance in Desy-Zeuthen that processes CTF data, and where we will get Rubin data and all of the other upcoming large streams. Thank you.